Welcome to this explainer from Forge College. I am absolutely thrilled to have you here. So we're going to do something a little jarring right out of the gate for this lesson on origins of the web, static pages, and early networks. We're transitioning from your recent capstone build where you just delivered that fantastic final analysis report on all those highly complex decentralized consensus mechanisms. Well, today, we're going to strip all of that heavy logic away. We're hitting the rewind button to look at the surprisingly simple, surprisingly manual, and, frankly, kind of primitive architecture of the early web.
Okay, let's pull up our engineering blueprint for today. We'll start with a welcome to the early web, then look at the billboard mental model, explain the core network protocols, see what going live in 1994 actually looked like, cover the limits of Web 1, and finally, prepare for interactive webs.
All right, Section 1. Welcome to the early web, from consensus to request response. To properly set the stage here, we really need to completely reset our technical baseline. Forget about smart contracts and global state for a minute. On one side of the architectural spectrum, we have the distributed consensus you just spent weeks studying. It's complex, it requires decentralized state coordination, and the network constantly has to balance safety and liveness. But on the exact opposite side, we have the early web. Just a dead simple request-response loop. Seriously, if distributed consensus is like a complex UN treaty negotiation, early request-response was a fast food drive-thru. The goal wasn't to agree on global state at all. The goal was literally just to quickly and reliably hand you a static document the second you asked for it.
Moving on to Section 2, the billboard mental model, designing the early architecture.
To really grasp Web 1 without getting instantly bogged down in endless networking jargon, it helps to imagine the early web not as some magical cloud of data, but as a physical, analog city. Look at how this maps out in our sketch. In our physical city, the billboard holding a printed poster, that's your HTTP server hosting a static file. The signpost physically glued to that billboard pointing you down the street is your hyperlink. The street map you use to find the billboard in the first place, that's DNS. And the postal roads and couriers carrying requests back and forth, well, that's your TCP/P routing. Servers were quite literally just billboards holding printed posters, sitting there, waiting for someone to drive by.
Now, the absolutely crucial point here is that this physical architecture carries some major, far-reaching implications for how information flowed. First off, the delivery unit is immutable. The poster is a fixed snapshot, right? It doesn't dynamically change for each viewer until the billboard owner physically goes up there and replaces it. Second, there is a single authoritative host. One specific owner controls that billboard and everything plastered on it. And third, discovery relies entirely on central mapping services. Because the content is just a static snapshot, it's incredibly fast to deliver and super easy to cache. But, and this is a big but, if you weren't listed in the central street directory, you were practically invisible to the world. It was basically like having a billboard buried in an underground cave. No one's going to see it.
Okay, Section 3. Core Network Protocols Explained, the Engineering Blueprint.
Let's see how all of this builds into the actual technical stack drawn out here on our network schematic. First up are the roads themselves, TCP/IP. That stands for Transmission Control Protocol and Internet Protocol. TCP/IP provided the underlying addressing, routing, and reliable delivery of bytes across the network. Honestly, think of it as an army of incredibly efficient postal couriers. It ensured that the specific bytes you requested reliably found their way across a massive web of global routers and made it right back to your exact machine. For sure, it's the most relentless, reliable delivery service ever created. Next, we have the MAP, DNS, or the Domain Name System. Let's face it, humans are famously terrible at memorizing raw strings of IP addresses. It's like trying to remember the exact latitude and longitude of your favorite coffee shop. It's just not going to happen. So DNS acted as the ultimate street directory. It translates those human-friendly names, like a .com, into the raw numeric IP addresses that the postal roads of TCP/IP actually need to route your request. And finally, we have HTTP, the Hypertext Transfer Protocol. This is the actual transaction itself. It's the standardized request-response language, where your browser basically walks up to the server and says, "Hi, please hand me a copy of that poster," and the server gladly obliges, returns a static HTML document, and then immediately forgets you ever existed. It's like a remarkably efficient but highly amnesiac librarian. And, that statelessness is exactly what made early HTTP so blazing fast, but also so incredibly limiting. Which brings us to Section 4, going live in 1994, a surprisingly manual workflow.
Let's ground all this high-level protocol theory in some stark reality, right? Imagine it's 1994 and you're an academic trying to publish your homepage. To get a page online, you had to follow 3 incredibly manual steps. Step 1, authoring. You had to physically write the HTML code locally on your computer in a basic plain text editor. Step 2, upload. You painstakingly transferred those exact files over the network using FTP into a specific public_HTML folder on an institutional server. And then step 3, discovery. Search engines as we know them today, yeah, they didn't exist. You literally had to send an email and beg a human web directory operator to manually list your site link so people could actually find you. Wild, right?
And heaven forbid you found a typo after you went live. You couldn't just click a convenient edit button on a clean web interface. No way. You had to open up your local text editor, fix the spelling mistake, completely overwrite the old HTML file, and then manually re-upload the entire digital poster via FTP. And because of network caches, you often had to helplessly wait hours for the typo to actually clear out of the system. Web publishing back then wasn't just coding, it was sheer manual labor.
Let's jump into Section 5. The limits of Web 1, why we needed more.
Now, this read-only model was absolutely brilliant for publishing academic papers, but it was incredibly limiting for actual user engagement. I really want you to ask yourself, in a world consisting purely of static, read-only billboards that instantly forget you the exact moment you walk away, how does a visitor ever leave a simple comment? How do you create a persistent user profile? Or, how do you even hit a like button on a post?
Well, the simple answer is they couldn't. Web 1 had absolutely no protocol for user accounts. It had a complete lack of dynamic application logic. There was zero shared state between the client and the server. And on top of that, there was massive centralized control over content discovery. Because Web 1 fundamentally lacked user-governed state at the protocol level, developers were forced to creatively duct tape centralized databases, cookies, and dynamic application servers on top of the network just to make things interactive.
And that leads us to our final section, Section 6, Preparing for Interactive Webs, the path to Web 2 and Web 3. All of that digital duct tape eventually became the massive architectural shift that we'll be breaking down in your upcoming Rise of Interactivity lesson. To summarize our engineering blueprint today, Web 1 successfully prioritized universal, simple document delivery over complex interactions. It intentionally separated delivery from state. And honestly, this was an incredible design choice at the time because it dramatically lowered the barrier to entry for readers and early publishers, which brought millions of people online. However, it heavily centralized control in the hands of major content hosts and a few key directory owners. The architecture made the web accessible, sure, but it made ownership highly concentrated. So, as you move forward in this course to analyze modern decentralized networks, I want you to keep this Web 1 blueprint in the back of your mind. Ask yourself this provocative question. When a new Web 3 protocol claims to remove centralized gates, does it actually restore user agency and state, or does it just hand the keys over to a brand new billboard owner? Understanding what the original internet lacked is really the only way to critically evaluate what new networks are actually trying to solve.
Thank you so much for joining me for this explainer. I really hope you found this breakdown as fascinating as I did. Make sure to visit forge.college to continue exploring these amazing foundational courses. Deep dive into our community and check out our other incredible Web 3 learning programs. I'll see you in the next lesson as we explore the rise of interactivity. Keep learning and keep building.